This video will wrap up our energy, our thermodynamics and chemical reactions video series by looking at two topics, redox reactions and catalysis. Let's start with redox. Redox reactions are chemical reaction sets consisting of two parts or two reactions. In an oxidation reaction, one substance, said to be oxidized, donates a high energy electron to another substance which is said to be reduced. So this high energy electron transfers energy from one substance to another. The oxidized substance loses potential energy, and the reduced substance gains it. The reverse reaction, or the opposite reaction, is reduction. And again, in reduction, one substance, which is said to be reduced, receives a high energy electron from another substance, which is said to be oxidized. If this all sounds kind of redundant, to a certain degree it is, there's two separate processes going on. The giving up of an electron by one substance, oxidation, and the reduction or gaining of an electron by the other. So in a redox reaction or an oxidation-reduction reaction, energy in the form of high energy electrons is transferred from one substance to another. In cellular respiration, cellular metabolism, one of the most important ways energy is transferred and then used to form things like ATP is through redox reactions. In cells, chemical reactions need to happen on the cell's timetable. Left to themselves, chemical reactions will happen randomly on their own timetable, and in some cases that may mean they won't happen at all. The cells need reactions to happen when they need them to happen, and they can make them happen when they need them through the use of a catalyst. Catalyst is a substance that speeds up a chemical reaction without actually being consumed during the reaction. The catalyst isn't really part of the reaction per se, and by that I mean it's not a reactant, but it's present and it influences the reaction and it makes the reactants become product faster. Regardless of whether a reaction ultimately stores or releases energy, a certain amount of energy called activation energy, or EA, is required to get the reaction started. I would liken this to if you want to burn gasoline in a combustion engine, you need the spark, the electrical spark from the spark plug, that small amount of starter energy to get it burning. Once the burning is going, once we have that input of energy, the reaction will continue to happen more or less on its own, but we have to have that initial input. To make this graphical, let's take a look here. On the bottom x-axis, we have time, or the progress of the reaction, and on the y-axis, we have what's called free energy, how much energy is available to do work. Here we have the starting energy within our reactants. This is how much energy will be present in our products. So it looks like a downhill slope, but in order for our chemical reaction to go from reactant energy on the left to product energy on the right, we have to go through this intermediate stage shown here. The difference between what we start with and this other amount of energy that's needed to get the ball rolling, if you will, is called the activation energy. So this graph shows how energy changes as we go through a particular exergonic chemical reaction. And this difference between what we started with and that peak is the activation energy, or EA. What catalysts do is they lower the amount of EA required. Think of it like this. In the boulder scenario a few videos back, there was a little block keeping the boulder from rolling. Now, even when the block was removed, we still had to push the boulder to get it to roll down the hill. That's the activation energy. But by removing the little block, it required less activation energy to get the boulder moving than it would have if the block was in the way. So again, to make this more chemically graphic, in the presence of a catalyst, the energy required for the transition state is maybe here. And so this is the path our energy needs to take, and there's less activation energy. The EA is smaller. It's more likely to get rolling on its own if there's less energy required than if there's more energy required. The most commonly used biological catalyst is what's called an enzyme. This is a type of molecule, type of protein that will be covered in a future video. As a student, I always personally found it challenging when I was first presented with the idea of catalysts to understand how could something be involved in the reaction but not be changed by it, or not be affected by it but speed it up. And then you're given, well, it lowers activation energy, which is a fairly honestly abstract concept, and it's frankly meaningless to the average person. When we go through the enzyme video later on that shows how enzymes act as catalysts, it will hopefully make a little more sense to you how enzymes lower activation energy without being part of the reaction, but while still helping it along. So remember, catalysts are substances that speed up chemical reactions without being consumed in the reaction. And we'll go into this in more detail soon.